david7santheater. You can contact us at david7santheater@gmail.com. Today I want to teach you the neuromuscular junction. We're going to talk about a lot about it. We're going to talk a lot about it, indeed. We're going to speak of the drugs. We're going to look at its structure. You're going to learn a lot. Neuromuscular junction. Just continue with me. You'll enjoy the videos. Okay, let's start right away. W7 Sunset Theater as our post banner, and don't forget to like us, subscribe for more and better videos, and don't forget to share the video to other students to also enjoy. Alright, the neuromuscular junction. We want to look at this structure first. Look at this first. If I have an axon of a neuron which is myelinated, as you can see, this is a Schwann cell and myelin sheath, node of Ranvier somewhere there. So this axon, this nerve, I'm just showing you half of it or part of it, and we'll send terminals, divide into several buttons, several terminals, which are distributed to different regions of the sarcomere. So you can see these are sarcomeres of the muscle. So if I have a muscle joined to a nerve, I'm calling it, to a neuron, I'm calling it a myoneuro or neuromuscular junction. So this I can try to magnify it to this one or this one. So it starts right from here. And if I have a muscle fiber having several sarcomeres, you can see the nerve terminals tapping into the muscle. So at this terminal, from a single point like this, I can get out this, and I'll have the presynaptic knob of the nerve, and this settles in a trough made by the sarcolemma or membrane of the muscle fiber. So this trough, then we have the axon. This is an axon terminal, the button. Okay, so look at this. We have the motor end plate. This is a part of the sarcolemma or muscle membrane, muscle fiber membrane. These are synaptic vesicles in the presynaptic knob, mitochondria, and the sarcolemma is folded. They are junctional folds. This increases surface area for attachment of the neurotransmitter. Okay, so look at this. This is the same thing. I have synaptic vesicles containing acetylcholine inside here. Then I have calcium channels through which calcium will enter from the matrix of the cleft. Then we have presynaptic membrane which has vesicles fused to show exocytosis. We have the postsynaptic membrane, that is the sarcolemma. Then we have acetylcholine receptors on the sarcolemma, and these are just junctional folds. Okay, so that's how it looks like. And synthesis and storage of this acetylcholine, which is going to be released. The mitochondria in the terminal buttons synthesize acetylcholine from choline, acetyl-CoA, ATP, and glucose in presence of the enzyme cholinesterase, or what we call choline transferase. So this enzyme is important and very important in forming acetylcholine within the mitochondrion. And once it's synthesized, the acetylcholine will be stored temporarily in vesicles in smaller packets called the quanta. And this quanta may be consisting of about 104 molecules of acetylcholine each quantum. Okay, so the neuromuscular transmission is the next thing we are talking about. How is the impulse transmitted from the nerve cause contraction within the muscle? There are a couple of sequence of events, and one is acetylcholine must be released from the nerve terminals. 2, must show some changes on the postsynaptic membrane, and these changes will end up developing an end plate potential Okay, and there from end plate potential we have a miniature potential. We have the from it we have the removing of acetylcholine by the enzyme cholinesterase. We're going to talk more about some few things here. These are common. We saw them in the synaptic transmission. And lastly, the insertion of action potential in the muscle fiber. So acetylcholine is removed. There's formation of miniature end plate potential, development of end plate potential. All these are sequence of events responsible for neuromuscular transmission. So look at this. End plate potential and development of action potential in the muscle fiber. If I have this curve here, you can see this is the potential with the time. When an impulse arrives at, let's say, at time 0, an impulse has arrived at this point. What will happen? There will be a weak end plate potential. This is what I call A. This rise here, weak end plate potential, and it is less than negative 60 millivolts. Okay? And after that, end plate potential will trigger propagating action potential. From end plate potential, now it will trigger an action potential to be propagated. And this is greater than negative 60 millivolts, as you can see here, and that is the B. Then the C is what we call the miniature end plate potential. That after action potential, we have a miniature end plate potential. Yeah, that is very small, but it is. We shall talk more about it in this very video. And look at this. Look at this. Development of the end plate potential. How does it develop? Because acetylcholine-gated channels are opening in the end plate membrane or sarcolemma, a large number of sodium ions will enter the muscle fiber from the extracellular fluid. Call it the cleft, from the cleft. Okay, and this will cause a local positive change inside the muscle fiber membrane. This is what we call the end plate potential. Just that local positive change. So the end plate potential is not propagated, but when critical level of around negative 60 millivolts is reached, it will trigger the development of action potential in the muscle fiber. That is true. This is the threshold value, okay? Negative 60 millivolts. So now what is it that we call the miniature end plate potential? Even at rest, a small quantity of acetylcholine are released randomly from the nerve terminal because of random Brownian movement of exoplasm. Yes, we talked about this in the other video, Brownian movement of exoplasm. So, small quantity of acetylcholine will be released still even at rest. So, each quantum of acetylcholine produces a weak end plate potential of about 0.5 millivolts in magnitude. So this is what we call the miniature. That at rest there is some release of acetylcholine. That's what we call miniature end plate potential. But now there is what they call the giant end plate potential. And this is due to more release of acetylcholine. That the end plate potential rises up to 12 millivolts, yet not sufficient to generate an action potential. Okay, so if we look at this, when we are at rest, some quantum being released, they are causing 0.5 millivolts. But there are times when the end plate potential rises to 12 millivolts, and yet it won't be able to cause an action potential. This is what we call a giant end plate potential. Okay, removal of acetylcholine. Acetylcholine released in the synaptic cleft stays for a short period and is removed within 1 millisecond by the enzyme acetylcholinesterase. which is present in the matrix of the synaptic cleft. And a small amount of acetylcholine will diffuse back into the nerve terminals from the synaptic cleft. Okay, so it is important to note that the rapid removal of acetylcholine prevents the repeated excitation of muscle fiber. This is very important to avoid spasms. Okay, so that's why acetylcholine steroids is very important. So there are drugs which stimulate the neuromuscular junction, and they have we have a group which have acetylcholine-like action. This will include methacholine, tobacco, nicotine. Yeah, this is common, and they act like acetylcholine and produce end plate potential, which excites the muscle fiber. However, these drugs are not destroyed or are destroyed very slowly by the enzyme acetylcholinesterase, so they will cause repeated stimulation and continuous action of muscle, thereby causing a state of muscle spasm. This is a clear point. Let's continue. The drugs that inactivate the enzyme. So the other drugs have been acting like acetylcholine. Now these drugs the next drugs are just inhibitors of the enzyme. Anticholinesterases, or call them drugs that inactivate the enzyme. These drugs like neostigmine, physostigmine, diisopropyl fluorophosphate, DFP, they stimulate the neuromuscular junction by inactivating this enzyme acetylcholinesterase, so that once it is inactivated, the acetylcholine released will not be destroyed, will not be hydrolyzed. This will lead to repeated stimulation and continuous activity of the muscle involved. But it is important to note that DFP lasts for several weeks. Thus, it is a lethal poison which can cause death due to laryngeal spasms. If the larynx gets spasms, might result into death. Okay, so let's talk. Those were stimulants. Now there are drugs which will block the neuromuscular junction, and these blockers the neuromuscular blockers will include one, curare, or call it the active principle of ditibutirarin. Yes, this is what they have in clinics. So curare, it prevents the neuromuscular transmission by combining with acetylcholine receptors. The acetylcholine released thus cannot combine with the receptors. That is how curare works. It binds to the receptors of acetylcholine. So the end potential does not develop, and the curare-form drugs are called receptor blockers. Curare-form drugs. The next drug is called bungarotoxin. Bungarotoxin is found in venom of deadly snakes and also blocks neuromuscular transmission by binding with the receptors of acetylcholine. The third drug is succinylcholine or carbamylcholine. These two drugs, they act like acetylcholine and cause depolarization of the membrane, but these are not destroyed by cholinesterases, so the muscle remains in depolarized state for a long time. Why am I calling them blockers? Because these drugs block myoneural junction by keeping the muscle in the depolarized state. When the muscle does not relax, then it can't be re-stimulated to contract. Okay, let's continue. The fourth drug is botulinum toxin. Botulinum toxin is derived from the bacteria Clostridium botulinum, and it blocks the transmission across the myoneural junction by preventing the release of acetylcholine from the terminal buttons of the nerve endings. No release of acetylcholine. That's how this bacteria is working, by its toxin. So now lastly, let's talk about the disorders of neuromuscular junction. 1. Myasthenia gravis. This is a common disorder, and is one where myoneural junctions are unable to transmit signals from the nerve fiber to the muscles, thereby causing paralysis of the involved muscles. No transmission of the signal from nerve to muscle. That is the gravis. And it's probably an autoimmune disease. In this disease, the antibodies are produced against acetylcholine-gated channels, call them receptors, present on the motor end plate, which destroy these channels. Okay? Yes. Thus, the acetylcholine release that the nerve terminal is not able to produce adequate end plate potential to excite the muscle fiber. And if the disease, the myasthenia gravis, is intense enough, the patient will die of paralysis, in particular paralysis of the respiratory muscles, because when respiratory muscles get paralyzed, the diaphragm and the like, no respiration and the individual will die. Okay? The last disorder of the junction is called Lambert-Eaton syndrome. The Lambert-Eaton syndrome is a disease, and antibodies are produced against calcium channels present on the presynaptic membrane, which destroy the channels. In the recent disease, we were talking about the receptors of acetylcholine. Now, the destroyed channels are those of calcium. Consequently, calcium influx into presynaptic knob is markedly decreased, and thereby release of acetylcholine is also reduced. Okay, and the scanty amount of acetylcholine will be not able to produce adequate end plate potential to excite the muscle fibers, producing muscular weaknesses. So the muscle will be weak in contraction, weak in activity. So due to damage of calcium channels. That is Lambert-Eaton syndrome. Thank you for following us. Don't forget to like our videos, subscribe for more and better videos, and share to other students to also enjoy our videos.